All right. So in the previous lecture only, I have discussed about the basic concepts of learning, intelligence, artificial intelligence, deep learning, machine learning, and what do you mean by machine learning? Its types we have discussed. Then for every type we have discussed about its limitations, and then we have overall discussed about the limitations of machine learning. Then we proceeded ahead with the deep learning, and I told you the history, how it has came into existence, and why we require deep learning now. And here at the last, in the previous session, I shown you a comparative graph between machine learning, neural network, and deep learning networks, that when we are in a large amount of data availability, then and if you want to perform your learning over it, so machine learning is something which we can't use. So here we need to work with your deep learning. So now, as per the architecture of neural network, we comprises of an input layer, an output layer, and a hidden layer. That's I already told previously. Whatever the computation needs to be done, that's done on your hidden layer. Okay, from input we give the input, and from output we receive the output. Okay, and obviously these layers consist of the neurons. Okay, neurons or nodes or perceptron or whatever you say, these are the units. Okay, and what these units have, if you just see that I give them as an input. Okay, so input can be like if I'm working with logic gates. Okay, so if I say I have two inputs, okay, one is 0 and one is another is 1. Okay, so I give input as 0 and I give input as 1. Then on output layer I am expecting something. For example, if I am working with the AND operation, okay, so I'm expecting, as per the combination of the bits, two inputs I need to give. So 0 0, if I apply AND operation over it, so the output will be 0. Okay, so here the architecture, as per the architecture of the neural network, it will be like something, one input layer, one output layer, one hidden layer, and the two inputs and one output. This will be the architecture. Okay, and in hidden layer, it will be something you have to decide that how many units we need to keep for our model to train well. In the last class, there is a question asked by Shweta also, sir, who decide how many intermediate layers we need to keep? See, the problem is with the deep learning, if we increase the number of hidden layers or intermediate layers, obviously the complexity is going to rise. Okay, your model will take a lot of time for its learning, and accordingly you should have the resources. Okay, so in order to check the complexity also, we need to decide how many layers we need to keep, intermediate layers, how many units we need to have in those layers. Okay, so as I told, input is something which we give. For example, here I took AND operation, so one combination 0 0, the output will be 0. 0 1, the output will again be 0. 1 0, again the output will be 0, and 1 1, the output is 1. Okay, as you know that how AND gate performs the operation. Now these are the inputs, we define them with x. Okay, so x is an input. Okay, as per the working principle of a neural network, we need to multiply this input with some weight. Okay, then we need to add this thing, whatever the result, w into x, we need to add a bias to it. Okay, and then this will be applied to your activation function, and will result into the output which we are going to show you on the output layer. So what is this weight? See, basically, a weight is a parameter within a neural network to transform your input data within the hidden layers. Okay, so it's a parameter. Weight is also a parameter, and bias is also parameter. Parameter means they are not fixed. they will be changing, okay, depending upon what you are expecting as an outcome. Okay, so within each node is a set of inputs. Every node, okay, yeah, there is a set of inputs, weight and a bias. These three values are all been available for each nodes, each units which are present in your layers. Okay, so here the point is, how does a weight work basically? As defined, to be very simple, weight controls the signal or the strength of the connection between the two neurons. Okay, it, very important line, it controls the signal or the strength of the connection between the two neurons. In other words, we can say that a weight decides how much influence the input will have on the output. Okay, because the point is, you are available with the result, you are going to perform the predictions. Okay, so I need to train my model according to what is expected. Okay, so outcome is there, you are having input, so you need to train your model accordingly. For every pass, as you have seen how I develop the model in projects also, for every pass your model is keep on learning, and there will be loss also. Okay, you have seen while your model train as per the epos number of passes, there is one parameter also, loss, validation loss, these two things. Okay, so there are losses. Okay, so what happens is, according to that I need to change my parameter, I need to change my weight, I need to change my bias in order to reduce those losses. That is why here it has been defined, weight controls the signal or the strength of the connection between the two neurons. How we are going to transfer the data from one neuron to the another neuron depends upon your weights. Okay, so initially we get started with some assigned weight, and when your model get it trained, adjustments, automatic adjustments keep on being worked on the weights. Okay, for both weights and the bias, these both are parameters. Okay, so if I would say how the weight work, see, um, within a neural network, there is an input layer which takes the inputs and passes to the next layer. This is we very well know. And the network layer contains a series of hidden layers that are called as a dense layers, which performs the transformations over the input data. Okay, within these nodes or the hidden layers, that weights are applied. Okay, because I already told, whatever the computation which you need to do, they will be done on the intermediate layers or the hidden layers or the dense layers. Okay, so these weights are assigned to the hidden layers. Okay, for example, if I just say there is a single node with they take an input data and multiply it with the assigned value and then add bias before passing the data to the next layer. Okay, before passing the data to the next layer, this is the activity is being performed on the input with respect to the weight and with respect to the bias. Okay, and this process is continuous within all the hidden layers, and then finally you share whatever the result to the is coming to the output layer. Okay, so as I told, wi into xi plus bi, this is for example is the complete equation, a linear equation something. Okay, as I have shown you here in the diagram. Wi, yeah, I would say W into X. I is the number how as per your inputs. So for example, I would just say X is an input, W is the weight, so Wx plus B. Okay, this is your operation you are going to perform on the hidden layers. Now the next thing is, just to be make much more precise, much more clear, what is the difference between weight and a bias? If both are the parameters, both the weight is deciding that what will be the strength of the connection between the between what neurons, strength. Okay, if it has been deciding this, so what is bias then? Okay, so both are learnable parameters. First of all, let me clear, both are learnable parameters. I told that when your model is going to learn, okay, initially we have given some weight and the bias there is available, and one there is one more parameter, learning rate is also been available in your model. Okay, so there is some learning rate also, so we give that particular rate and the model start learning by the rate which you are been giving. So initially we given, if for every pass there is some adjustment as per the losses, because ultimately I need to reduce the loss. Okay, so as the training continues, both the parameters are adjusted towards the desired value and the correct output, because you are already available with the output. And if you are not getting the expected output, what will happen, they are automatically adjusting their values. Okay, automatically they are adjusting. Okay, so in order, why? Because if there is a difference between the accuracy which you are achieving and the output which you needs to get, okay, if there is a difference, that means obviously there is a loss. Okay, so we will be minimizing our loss, so accordingly the weights are being adjusted. All right, so the two parameters differs in the extent of their influence upon the input data, because whatever you are going to do, you are going to work upon the input data. See, bias represents how far the predictions are from the intended value. This is the bias. How far we are. What is the difference? This is your output and this is you are getting. Difference between your predicted value which is incoming and the exact value which has been available on the output. How far we are from it. That is the difference. That is called as a bias. Okay. So bias make up all the difference between the function's output and the intended output. Remember, very, very important thing which I'm telling you. Okay, so this is what a bias is called. Difference, your prediction and the actual output, difference between these two, that is called as a bias. Whereas a high bias makes less assumptions about the form of the output. Obviously, if the bias is high, that means we are in a big loss. Okay, there's a great difference between them. Weights, on the other hand, can be a strength of the connection. As I already told, that weight affects the influence a change in the input will have upon the output. What is the influence? What this being a correction for one neuron to the another neuron. Okay, it's been influencing that if this is my value, if a current neuron is having certain value, if I transform that value to the another neuron, how much it will affect it to it after transforming this data to the next neuron. Okay, so here a low weight value will have no change on the input. Okay, if the your weight is low, so obviously if you multiply this with the x, so there is a minimum change in the initial x. Okay, so there will be no much changes in the input. And alternatively, if you take the larger weight, obviously it will have a big impact on the output. Okay, because if we give on the higher weights, so as we keep on transforming next to next to next, obviously that will be giving you there's no significant change in the output. Okay, so these are the definitions of the weight and the bias. I hope it's been clear to you. Any doubts, please let me know. Is it clear?
So they are more like hyperparameters, right? Like
Yes,
how we have in machine learning.
yes, yes, yes.
So it's like, do we have methods also for it? Like example, we had grid search CV or random search that way in machine learning,
See,
right? So do you have?
I told that yes, there are certain parameters when
Okay,
we fit, we compile our model, we fit the data to the model. So in the
mm-hmm.
compilation process also, okay.
Okay,
So we are having certain other parameters. I told that there is some
okay,
learning rate and
yes, yes,
okay. So these are all put an impact.
okay,
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 on these. So
all right.
here weights control the signal, and bias is the difference between your expected and the actual output. Okay, so the next comes is the activation function. Okay, because as you have performed this operation, okay, you need to apply this to an activation function. So now, very important topic, activation functions. See, activation function calculates a weighted total and add bias to decide whether the neuron should be activated or not. Okay, if I there is a requirement of activating a neuron, or there is not an requirement of activing making a neuron active, so it depends upon your activation functions. Basically activation functions are non-linear. Okay, they're non-linear in nature. Okay, so in this we are going to check why it is required activation function, why it is in a demand that we need to make our neurons active, and what function you need to select. This is what we need to check in this particular segment. So a neural network without any activation function is basically a linear regression model. That is straightforward linear regression. Okay, as we do follow the approach in traditional machine learning algorithm as a linear regression. Without activation function, your neural network is as same. Since the functions perform non-linear computations in the input of the neural network, we want to do this task to have a complex. Okay, so if you don't have any activation functions, then it's just a simple linear regression. But if you are having a non-linear activation functions, this is very much helpful for you to perform the complex task, and here is the working of an activation function. Okay, so as I told, that w1 x1, and this you have given as an input, so w1 x1 plus the bias. Okay, plus bias. And here you have one more, that is the basic input, initial input x naught, that is multiplied by b. So w1 x1 plus b into x naught. Okay, and this you have given to a particular function sigma. Okay, this is an activation function, a equal to sigma z. Okay, so if I don't take here as x naught, so that will be straightforward, that is a b. Okay, initial I will not take, so this will be just like as a b. Okay, so w1 x1 plus a b, just give it to the activation function and check what result you are getting it. The value of activation function is between 0 to 1. Okay, here you can see it is between 0 to 1. Okay, so the activation function transforms your input on a non-linear way. Okay, let us explore some more things related to it, because we need to focus much more on activation functions, and we will explore here each and every type of explore your activation function. As per I told above, that here weighted sum of the input is transformed to the output. This is what, if someone asks what does an activation function do, you will say it transforms weighted sum of the input to an output, from node to, from one node to the another node. Okay, I am available with the node. The task which is being done on the node is this only. Okay, w into x plus b, there is an activation function there. Okay, whatever the result is coming, just transform it to the next node. Okay, then whatever the, then again we perform the same task, whatever the output is coming, transfer to the next node. So they are also called as a transfer function, because here transformation is been going on. It may also be called as a squashing function also. And these are non-linear in nature. Again, the same thing as I told about, I don't want to make my model as a linear regression model only. Okay, so this is non-linear in nature, and it follow the property of non-linearity. Okay, now the case is choice of activation function, because first we'll study how many activation functions are there, then we'll look out for the choices. So the activation function is used within or after the internal processing of each node in a network. Okay, you have also created your architecture, you have created your model, and in my projects also I do define that take model equal to sequential. Okay, then I start preparing the layers in that particular model. I take a dense layer, I take dropout layer, I take flatten layer. There are many layers, I will explain each and every layers in this course also. Okay, and meanwhile I also keep activation equal to activation function. I will just take, sometimes I take ReLU, sometimes I take Sigmoid, sometime it may be 10h, sometime it may be Softmax. So what are these are, who decides which activation function you need to take? Okay, so network has three types of layers. We know input layer, hidden layer, and output layer. These are the basic layers for a neural network. Okay, all hidden layers have the same activation function. Whatever the hidden layers we are having, they are having the same activation functions. The output layer will typically use an activation function from the hidden layer and is dependent upon the prediction required by the model. What kind of output you are expecting, that activation function has been present on your output layer. Remember very very key points. To be general, all hidden layers have same activation function. Point number 1. Point number 2, the expected output which you require on the output layer, This is been something which we need to decide what activation functions we need to keep. Okay, so activation functions are typically differentiable, meaning they are having first order derivative. Okay, first order derivative, delta by delta derivative. Okay, and here neural network typically trained this by using back propagation algorithm. And why this has been happening? Because the reason is, I already told above also why it is derivatives. There is a differential calculus. Derivative is a differential calculus, and the reason is I need to adjust my weight and the bias. That is why I'm taking the derivative. So derivative will be taken with respect to your weight, delta upon delta w, something like that. Okay, I need to adjust my weight because the reason is I need to train my model according to the output which has been we have given as per the data. Okay, so my main concern is to reduce the loss. So as on your model get on training, learning, the main goal is to reduce the loss and improve the accuracy. Okay, but accuracy, it's not like that just make it as 100%. No, it's not like that. For that purpose there is one thing, that is the dropout. Whenever it happens that accuracy is going to be increased too much, okay, then we are using dropout to ignore some of the neurons for the training. Okay, so that I will let you. I have also discussed this thing in my projects also. I just repeated this. So what is this derivative? I am going to do this because the reason is I need to keep on adjusting my weights. Adjustment, and adjustment will be done on the basis of gradient descent. Gradient descent. So gradient descent algorithm or a technique I have always used. What optimizer you need to take, Sir Adam? Every time when you compile, you take optimizer equal to Adam, because Adam is a popular gradient descent algorithm. Okay, so Adam optimizer, someone which uses Adam algorithm, and it's actually this algorithm only. So it iteratively calculates the next point using gradient at the current position. I need to calculate the next point, and I'm checking the gradient at my point and scales it by a learning rate. Okay, and scaling, there is a scaling with the help of a learning rate. Whatever the learning rate which you are going to give in your model, that is 0.001 or 0.0001, whatever the learning rate you are giving, and subtract the obtained value from the current position. Okay, and subtract that obtained value from your current position. That is the gradient. That is actually the gradient. Okay, it is subtracts the value because we want to minimize the function. Ultimately we need to minimize the loss. That is what it has been telling you. So gradient descent iteratively, for every pass it calculates the next point using the gradient. Okay, next point I need to what should be the next point will be, every time it is going to check with this algorithm. Okay, and keep on updating itself according to the learning rate and subtract the obtained value from the current position. Okay, back propagation, this term is also been used here. See, it is an algorithm used for supervised learning for artificial neural networks using gradient descent. So whatever been happening here on the gradient descent, this is what actually called as a back propagation of errors. Back propagation of errors, again the same thing as I always repeating, I need to reduce the errors. So back propagation of errors is to minimize your errors. Every time, every point I need to calculate the next point, then next point, then next point, by using gradient descent algorithm. Iteratively I need to calculate all these. Okay, so given in an artificial neural network and an error function, the method calculates the gradient of errors function with respect to the neural network weight. That is what I told you, delta upon delta w. Delta upon delta w. So delta upon delta w, for example I would say x2 minus x1, then delta upon delta w, x3 minus x2, then delta upon delta w, x4 minus x3, and so on. So this is what we are keep on calculating the points. Okay, with respect to the weights. Okay, so this is called as gradient descent. Okay, and followed by the approach called as back propagation of error. So this is how we perform the adjustments. So in an ANN and error function, the method calculates the gradient of error function with respect to the neural network weights. Okay, whatever the error has been coming, we are uh, calculating is gradient with respect to the weights. Okay, and we are just trying to reduce those errors. There are various types of activation functions which are available in the neural networks, and these activation function work on the hidden layer. Okay, and the output layer also. Okay, so we need to decide what to be done. So a hidden layer does not directly contact with the input data. Okay, hidden layer does not directly contact with the input data and produce the outputs for the model, at least in general. In general, there is no directly. Typically, a neural network has zero or more hidden layers, as I already told. For example, if you are creating a simple artificial neural network, then there is one hidden layer. But if you are considering a deep learning, then they are having multiple hidden layers, more than one hidden layer. Ultimately, there will be a rise in the complexity also. Okay, this is what been happening. Now the case is, in order to get access to much richer hypothesis, let's see what these activation functions are. The basic activation functions are your ReLU, that is rectified linear activation, logistic, that is a sigmoid function also, and hyperbolic tangent, that is tanh. These are the activation functions. Okay, so if I talk about ReLU, that is rectified linear activation function, it is very common activation function which has been used in the hidden layers, and I already told you what this ReLU function do. See, ReLU function is a very easy function, and if you supply any data inside this ReLU function, it is going to give you the output as, if your data is less than a 0, that means if you're supplying a negative value to this function, it will give you output as 0. And if you are supplying the positive value to the ReLU function, then it will be going to give you the same result. Okay, so here the ReLU function is something like this: max x 0 comma x, 0 comma x, maximum of 0 and x. Okay, if there is a negative value, it will return 0. If there is a positive value, then it will return you x, the same value. Okay, this ReLU function is very common because it is simple to implement, as I told that what does this function do, and it overcomes the limitations of other activation functions such as Sigmoid and Tanh. We will see both of them, Sigmoid and Tanh. We will also see these activation functions. Okay, so here is your mathematical this your mathematical thing for your ReLU function. This is how this function has been described: max of 0 comma x. Okay, and if you want to show the graph of your ReLU function, so here is the graph. Okay, so till 0, whatever be the negative value which it has been accepting or giving, it's giving you the result 0. And when you started giving the positive value, you can see there's a straight line. There's a straight line. So this is a graph of ReLU function. Okay, so when we are using this ReLU function for the hidden layers, it is good to practice to use he normal or he uniform weight initialization. That means here the input data has been in a range of 0 to 1. Okay, so this is the case when you are using the ReLU function. It is suggested. So, do you understood the ReLU function? Any doubt here in ReLU function? Please let me know. And again, this is basically, how to say, we use non-linear activation functions. Non-linear activation function. Okay, as in the concept says, non-linear activation function. Okay.
Basically, it depends on our data.
Basically depends upon data. Yes. Basically
Okay,
depends upon data. Okay, but most of the cases we are using ReLU function in the hidden layers.
okay, sir.
Okay. Now the next layer in hidden layer, the function which you can use is a sigmoid function. Okay, so sigmoid function, I wonder you very well know about the logistic regression. Okay, logistic regression, basically it have this sigmoid function only, or rather it's say sigmoid activation function is a logistic function itself. Okay, so what happens in that logistic regression that is used for the classification in a traditional machine learning algorithm? Here also the function takes the real values as input and outputs in a range of 0 to 1. Okay, the range is 0 to 1. The larger the input, or the more positive, the closer the output value will be to 1. Okay, as much as large the value of your this function, that is your input, you're very much close to the output, and smaller your input, that is much more negative, closer the output will be to be 0. This is a great understanding. This is something which we are going to understand. That means it's clearly showing that you are going to perform some classification. This is certainly a classification. So if you are having a problem statement related to the classification, the kind of activation function which you need to use in your preparation of the model in hidden layers, that will be your sigmoid function. Okay. However, we'll see. We'll just check out what other possibilities are. But here we are just understanding. Okay, classification, because it's compatible with like logistic. So sigmoid function is represented as 1 upon 1 plus e to the power minus x. This is the logistic equation only, and or I will say it's a sigmoid activation function equation. Okay, 1 upon 1 plus e to the power minus x. Okay, so here this is the thought what happens in a sigmoid function. Its shape is nearly like s shape. You can see here is the s shape, because we are using exponential here. Okay, so its shape is just like s only. Okay, you can see s shape sigmoid function. Okay, so when we are using the sigmoid function for the hidden layers, it is good to practice Xavier normal or Xavier uniform weight initialization. Okay, and we can scale the input data for the range 0 to 1. Okay, for the training. Okay, so whatever be the cases are where we need to use your ReLU function, whether you need to use your sigmoid function. See, in case of ReLU function, you might have a doubt, sir. This is looking like a linear, sir. This is a linear equation, isn't it, Shweta? Isn't it a linear equation from here after 0?
Yes, sir, it does look like that.
So what kind of problem we are going to calculate here if we are creating this kind of if you are using this activation function? So what kind of task we are going to perform over the using deep learning?
Classification.
Are you sure? Classification?
Mm,
Classification or regression? What do you think?
yeah.
See, in case of, I have
Yeah.
already told initially, what is the task of your activation function? Where without an activation function, a neural network is just like a linear regression model. So
Yes.
if you are not having an activation function, or if you are having an activation function also, but it is behaving like a linear way, so what should be the task? What do you think?
Regression.
Obviously, okay, if you want to have some predictions, obviously, so we are using the ReLU function here. But in case if you are going to perform some what kind of task, if you want to have some classification problem, so here is something which we can, because they clearly made you understood that if your input is larger, so we are closer to your output value is 1, and if your input is negative, so we are closer to output as 0. Oh, this is how it works. Okay, so this is a sigmoid function, and it depends whether you need to use a sigmoid function over the hidden layers and whether you need to use your ReLU function inside the hidden layers. Okay, you'll see ahead. Now, the next is your 10H hidden layer activation function. Okay, why Shweta you said, sir, it's been used for the classification ReLU? Why? What made you to tell this?
So because it resembles, as you said, it uses a sigmoid function, right?
Uh-huh.
So I thought it is used for classification.
Okay. Okay. Now, the next is your tanh activation function, that is hyperbolic tangent. Hyperbolic tangent. So again, tan function like trigonometry, we can see that its equation, or I would say its expression is given like this: e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. This is how we can represent a hyperbolic tan function. Okay, tan activation function. So what does this do? See, it is very similar to the sigmoid function, and it is also having a same, that is like S shape only. But difference is what which is having a better S shape, whether it is steeper or whether it is denser. What kind of S shape we are having? Okay, so what does this function do? The function takes the real value as an input and the output in the range of -1 to 1. Previously, what kind of input they are taking? They are taking the input 0 to 1 This function ReLU, what kind of input it has been taking? What kind of input? It is taking the input, if it has been negative, okay, anything, I'm not strict, I'm not strict to just only -1. Any negative input it has been taking, it is giving the result as 0, and any positive input it is taking, it is giving you the same value. Okay, but in case of your sigmoid function, it takes the input and output between the range of 0 to 1. Understand, and this is what you're just performing some, what kind of task. This is just classifying 0 1 0 1 inside your hidden layers. However, the final output layer, the kind of function which we need to use on that particular, that is something is the resultant. But initially intermediate, I'm just making you understand, okay, what is happening here. Okay, any doubt, please let me know.
No, sir. No doubt.
Okay, so here your hyperbolic function, tan hyperbolic function, it's been taking the input and the output range between -1 to 1. Okay, so larger the input, we are closer to the output, same thing, and smaller is the input, that is more negative, then we are closer to the output, -1. Okay, so -1 to 1, this is what the hyperbolic activation function, its value lies. So you can see here is the expression I have already told, and here is your graph. It's just like again s. So whenever we are having some expression in e to the power x or e to the power -x or something, obviously you will get such kind of curve. Okay, so this is your hyperbolic curve, hyperbolic tan curve. Okay, so these three functions are the basic functions which we used in our model, okay, in deep learning. Now the point is how to choose. Who will decide that what activation function I need to take? See, a neural network always have the same activation function in all the hidden layers. Please make this thing store somewhere in your memory. Okay, same activation function in all the hidden layers, and the activation function on the output layer may be different. That's not mandatory. Okay, so sigmoid function was the default activation function in 90s. Okay, till 1990, sigmoid function is a by default function when we are working on these layers. Okay, then in 1990s to 2010, 10h was the function as a by default. Okay, so sigmoid and 10h functions, these are by default activation functions in the previous years, but we found problems during training. That is vanishing gradient problem. That means when you are calculating your gradient descent, that is they are vanishing. Okay, that means they are much more now equal to the 0. Okay, so they will be giving you a tough hurdle in adjustment of the weights and the bias, and ultimately I need to reduce the errors. And if errors are not reducing, obviously your model accuracy is being going to effect. Okay, so these two are giving some issues. So later on we choose your ReLU function to perform the task. Okay, so modern neural networks with common architectures such as multi-layer perceptron or convolution neural networks, they use a ReLU function and its extensions. Okay, this function, and there are certain extensions of this function also, ReLU. Okay, so now you might be knowing that what could be the issue why we reduce the use of these other activation functions, because when they are going to be extension, when you are getting a zero value for the gradients and all these things, so now obviously your there will be difficult to adjust the loss. Okay, and the loss will be same, or it will be like not been tackled, so accuracy will be going to affect while your model training. So if you want to train our model in a good way, the hidden layer should be following your ReLU activation functions. Okay, so recurrent neural networks still commonly used in RNN. So basically, I told in the previous lecture also that your deep learning is having two kind of it divided into two categories. One is the CNN, one is the RNN. So CNN, that is convolution neural network, that is basically works with the images, and recurrent neural network that works with the text and other stuff. Okay, so a recurrent neural network, that is for example LSTM, long short term memory. In my projects, most of the time I use as LSTM also. So they follow this approach, that is 10H and sigmoid activation functions. Okay, and if I talk about where to use what activation functions, so if you are having multi-layer perceptron ReLU activation function, if you are having CNN, if you're having a CNN architecture, if you're using CNN, then use ReLU function. And if you are using recurrent neural network, then you can use 10H and sigmoid function as an activation function for the hidden layers. This is what you need to do. And it's been mentioned here in this diagram also. Network type, what could be the network type? This is what you can use. Okay. So here we discuss what an activation function is, what type of activation functions are, what they basically do, what is their equation of the activation function. We also decided what to use on the hidden layers. Okay, now the case is what activation function you use on the output layer. Now this is something, the decision making layer, that is output layer, what to use there. See, the output layer is a layer for the neural network which directly produces the output for the prediction. Whatever result you are expecting, you are going to give on the output layer. Okay, so all feed forward neural network models have an output layer. Feed forward neural network. So, what is this feed forward neural network? A artificial neural network in which nodes do not form a loop. There is no looping. That means if you have created input layer, hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4, hidden layer 5, output layer. So whatever I transform here from the input layer to the hidden layer 1, hidden layer 1 will give the output to the hidden layer 2, hidden layer 2 will give the output to the hidden layer 3, hidden layer 3 give the output to hidden layer 4, hidden layer give 4 output to the hidden layer 5, and hidden layer 5 give the output to the output layer. That's it. There is no loop back. There is no chances that I backtrack to hidden layer 2 to hidden layer 1. No, there is no chances. There is no chance hidden layer 3 to hidden layer 2. Okay, just we need to move ahead, forward, feed forward. We are feeding forward, we are feeding the data to the next layers, feeding forward. This is the name itself suggests feed forward networks. So this type of neural network is also known as multi-layer neural network, in which we only pass the data ahead to the next layers, nothing backward. Okay, so during the data flow, the input receives the data and which travels through the hidden layers and exit through the output nodes. And I have already told you about what it do, and this line also mentions the same. Okay, as we are having three activation functions, that means linear function, logistic function, that is sigmoid function. There is one more function which can be used in the output layer, that is a softmax. There is a softmax function which we can use in the output layer. So we can use linear function also. Okay, that is your uh, um, linear function, then sigmoid or your logistic function, and one more additional, that is softmax function. Okay, so what these are: linear output activation function, that is identity function. Identity. Okay, linear activation function is an identity that is multiplied by 1 or no activation. That's it. Okay, so this is because the linear activation function does not change the weight sum if the input in any way, and instead returns the value directly. Okay, so the linear function or identity. Okay, what do you mean by identity? What do you mean by identity? What kind of operation this linear function is going to perform here? Whatever we are getting, whatever we are getting from the hidden layer, we are just multiplying it by 1, and that's it. We are supplying it via the output layer. That will be the output. That's it. That is a linear output. Are you getting my point? What I'm saying? Whatever you are getting from the last dense layer, just multiply it by 1. That's it. This is the identity. And just apply it. That is output. That is a linear activation function. That is a work of linear. Okay. However, this is because the linear activation function does not challenge the weighted sum of the input. In this way, instead returns the value directly. So whatever the value which you are getting after the final calculation, whatever you are getting after the final calculation, the last dense layer, whatever your last dense layer is giving you, the output to the output layer, that's it. Finish. That will be the only output, because there is no challenge. We don't give any challenge to the weighted sum here. Wait,
So
no,
what
no,
is the
no.
use of this skill?
See, what is the use? Basically, the point is, if you want a result, that we will, how can I say, if you want a result which don't require any changes at the last. Okay, just we need to
Okay.
just give directly as an output to it on the output layer. Okay, so that is why we are using this identity function or a linear function. Okay, so
Okay.
that is the purpose. That means we don't require any activation. For example, if you are working with your regression, again the same thing. If so, going to do some predictions, and after all the hidden layers, okay, you get the result. What is going to be predicted? Just multiplied by one. Ultimately, only the use is I need to keep something. I need to keep some activation function on my layer. Okay, so if I don't want to do any change, so just keep your keep your linear activation function there. Okay, just
Okay, sir.
but keep something. Okay, but keep something on the output layer. Okay, so for that purpose I've used a linear activation function on the output layer. So just multiply by one and just produce the output. That's it, no changes. Okay, there is no change in the weight, so something which don't do any change on the weighted sum. That's it. Okay, next one is a sigmoid. Sigmoid I have already told. Okay, sigmoid function I have already described you above what does sigmoid do. Okay, and between 0 to 1, obviously it's been used for the classification. Okay, obviously it is just like a classification. So here again, if what does linear, as your function is linear, the point is very much said, clearly said, prediction. Okay, straightforward prediction. Linear function is just straightforward for the prediction. So what are the prediction which you have got via the computation over the dense layers, just put it as it is on the output layer. That is linear. And if you want to do some classification, if your problem is related to the classification, use sigmoid function on your output layer. Okay, so when we do work upon projects also, and when I define that, okay, we have used sequential model, we have taken this much in, this is the input layer, this is output layer, I've used this activation function. But unless and until you are not clear with the concepts of these, so it is a very difficult task for me to explain each and everything in a 3 hours. Okay, I'm really happy. I'm really glad that you guys have joined this course. And are you finding it interesting or not?
Yes, sir.
Yes, it is.
Okay, so that is why if you been learn from this, then obviously that will be easier for you to understand that how many layers I had need to keep, how many units I need to keep, and what activation function I need to keep on the hidden layer, what activation function I need to keep on the output layer. So now your base will be getting stronger. The next activation function is a softmax function. Okay, let's see what does softmax do. See, softmax function outputs a vector of values that sums to one. Okay, that means I'm not restricted to any just like a simple predicted value, or I'm not restricted to any some classified value. There is a output of vector of values, and all of them will be result to one, and that can be interpreted as a probability of class membership. That is a multi-class thing, something related to the multi-class. Okay, let's see how this thing works. Softmax is a software version of argmax. Okay, what is this argmax? See, what is max? See, what is max? Let us just describe first about max. See, max function, if I am having two values, 2 comma 3. Okay, what will be the result from the max function? 3.
Three.
Now, for example, I have created a list 2 comma 3. This is a list. Okay, and your list is just like a equal to 2 comma 3. This is your list. And if I need to print the value at index 0, a0, okay, a0, what will be the result?
Two.
2.
2. And a1, a1, the result will be 3.
3.
So if I talk about argmax function, see, argmax function will return you the index. It will return you the index. If I just say argmax 2 comma 3, the index of 2 will be, 0, and the index of 3 will be 1. This is what has been written by the argmax. So this softmax function is a software version of argmax. Okay, this software version of RMS that allows a probability like output of the winner take all. What is the probability that I am been getting the result as 2, or I am been getting a result as 3? What is the probability? Okay, and it will sum up to 1. As already I know, probability cannot be greater than 1. Probability always lies between 0 to 1. Okay, so what is the probability of getting the value as 2? What is the probability of getting as 3 or whatsoever? So this has been done with the help of a Softmax function. Winner takes all. Okay, so here as such the input of the function is a vector of real values. I put vector. Okay, so I will put all these vector format. I will give the here as an input. Okay, and output is a vector of the same length, same whatever the length of your vector, same length will be the output, and the sum of the probability will be the sum of uh, the probability of all of them. For example, the probability of coming of 2 is zero point 0.4 and the probability of coming of 3 is zero point 0.6. So it will be like the result will be the new vector, the resultant vector will be zero point 0.4 comma zero point 0.6. Are you getting my point or not? You got my point?
Yes, sir.
This is
Yes.
what Softmax do. Okay, so it has been calculated like this: e to the power x upon sum of e to the power x. This is the expression for the your Softmax function. So where x is a vector of outputs and e is a mathematical constant, that is 2.7. The value of exponential is something like 2.71. Okay, in maths. Okay, so here the target labels which we use to train our model with the Softmax activation function in the output layer will be the vectors with 1 for the target class and 0 for the other classes. Okay, so if you are having the probability nearer to 1, for example 0.8, 0.7, 0.75, so that means you are much more near to your target. And if you are having the probability of the values like zero point 0.3, zero point 0.2, that means you are away from your away from, that means they are other values. So target labels used to train a model with a Softmax activation function in the output layer will be the vectors between with 0 for the 1 for the target class and 0 for all others. Okay, for all others that will be 0, and for a target, expected target, it will be 1. This is how we are going to train our model with the Softmax activation function. This is how we need to train. Okay, so again it will be like it will be based upon the classification. So Softmax is also been used in a classification problem. Okay, not for the prediction, for the classifications basically. Okay, now how to choose output activation function. Now again this is what we need to understand how to choose. For example, you may divide the prediction problems into two categories, that is the prediction of a categorical variable, that is a classification, and predicting a numerical variable, that is a regression. Obviously we are having two problems, one is a prediction, one is your classification. In case of regression, one node linear activation function, because obviously as I told above also, linear activation means whatever the computation has been done over the hidden layers, you need to multiply one with that and you need to just generate the output. That will be obviously a prediction. One node, that is a linear activation function. Regression, okay, predicting a numerical value. If you are going to work with a numerical value, multiply it by 1, that is the regression. Okay, if your problem is a classification problem, then there are three main types of classification problem. Okay, three main types of classification problem. Predicting a probability is not a regression problem. If you are going to predict the probability of an occurrence of an event, that is not at all a regression. That is not at all a regression problem. It is a classification problem, because the point is we are expecting that this will occur or that will occur. So it is a classification problem basically. In all the classification, your model will predict the probability of a class member. For example, it is a multi-class problem, cat or a dog classification problem. If you are taking for the images, so it will just check the probability that this image is going to be a cat image or this image is going to be a dog image. Okay, for example, the probability that example for the each class. Okay, for 80% it is a cat, at 20% it is a dog. See, this is a machine. You are a human, you can say that this is a cat and this is a dog, you can differentiate, but we are now making a machine to learn. So machine will learn and give you the result as per the probability. It will give you the chance. Don't think there, see, internally there is a chance that machine is giving you, okay, I have learned by your data of images, and after my learning, this is what I assume, that there is a chance, 80% chances, that the image which you have input from your side is a cat, or rather it is a dog. Okay, so this is what happens, and for that purpose you need to use sigmoid function, or rather you need to use softmax function. If you are having a classification problem, you need to use sigmoid or softmax. Okay, and if you are having a regression problem, you need to use linear activation function at the output layer. Now you got my point. If I, in my model, if I use a linear activation function, for example output, if I just use ReLU, you will say, sir, it's a regression problem, I'm going to predict something. Okay, and if I'm using sigmoid or shortness function at the output layer, the point is clear, I'm going to perform any classification problem. Is that clear or not?
Yes, sir.
Okay, so it can be like anything: binary classification, it can be like multi-class classification, it can be multi-label classification. If we talk about binary classification, that means we are having one node, sigmoid function, sigmoid activation function, one node, sigmoid activation function. Understand what kind of classification I need to do. Only one node at the output layer. Understand, one node, only one node is available on the output layer, and sigmoid function takes between 0 to 1 as an input and 0 to 1 in the output. 0 to 1 in the input and 0 to 1 in the output. This is what sigmoid function performs. So only one node will be available on the output layer. If you are having just binary classification, two class only, either dog or either cat, that's it. Multi-class, if I am having much more classes, dog, cat, cow, horse, whatever be your animal, so one node per class, that means I should have four nodes available in my output layer, and I will be using shortness. Why? Because it will give you the probability. Okay, for example, if I am giving a cat image as an input to my trained model, so the probability will be something like that: zero point 0.1 for dog, for example, zero point 0.2 for horse, zero point 0.3 for cow, and zero point 0.7 for cat. Are you understanding what I'm saying? You got my point or not?
Yes, sir.
That is multi-class classification. So higher will be the probability of the cat. Okay, that will be like 0.7 or 0.8. Okay, and remaining all will be less. Multi-label classification means one node per class. Sigmoid activation. Here the sigmoid multi-label. Multi-label means, multi-label classification means, if there are two or more mutually inclusive classes, that means mutually inclusive means, what does this mutually inclusive means? What is this mutual inclusion? Is there any dependency between these two? Mutual inclusion.
Yes, sir.
Okay, so in case if there is some interdependency, so for that purpose, I have to use your multi-label classification, and that means one node per class. Again, one node I need to take for that also. But the function which I'm going to use is a sigmoid activation function at the output layer. Okay, this is what I need to take, and here is your the diagram. That is, if you're having a problem type like classification, binary, multi-class, multi-label, sigmoid, binary, sigmoid, multi-class, softmax, and multi-label sigmoid function. For regression, linear activation function. That's it. No more things you need to cover here. Okay, so for this lecture, any doubt? Any of you girls are having doubt? Do you understand the activation? This is in this lecture we have completed our activation functions.
Sir, can you repeat this last one, multi-label
See,
classification?
multi-label classification. Okay, in case of multi-label classification, we told that if there are two or more mutually inclusive classes, mutually inclusive classes means if we are having some common parameters. Okay, common. So if we are having some common parameters between them, that is called as mutual inclusion. See, in sets, do you study na? Mutually inclusive and mutually inclusive and
Yeah.
exclusive. Okay,
Yeah.
so what happens in that mutual inclusive events and mutual exclusive events? What happens in that? Okay, for example, if I say, because this is certainly probability, because in case of classification it deals with the probability. If here you have been told mutually inclusive classes. Okay, if I talk about mutually exclusive events, that means those events which do not occur at the same time, that are mutually exclusive. Those events which do not occur at the same time means, at the same time this cannot be this and this also. Okay, at the same time,
Okay.
if you have given some input, तो वो it should not be cat also and dog also, वो दोनों नहीं हो सकता एक ही समय पर,
Yes.
या तो वो cat होगा या तो वो dog होगा, ये exclusive है.
Hmm.
This is called as exclusive. तो और inclusive क्या होगा फिर? What does this inclusive means? यदि मैंने बोला एक्सक्लूसिव में ये है कि दोनों एक समय पर नहीं हो सकते, तो इंक्लूसिव के अंदर क्या होने वाला? व्हाट शुड बी इन इंक्लूसिव? व्हाट आर म्यूचुअली इंक्लूसिव इवेंट्स? तो इंक्लूसिव इवेंट्स में ये होगा कि ओवरलैपिंग, मैंने क्या बोला, कॉमन. ओके, तो आपको कुछ फीचर्स कॉमन मिलेंगे, यू विल गेट सम कॉमन फीचर्स, दैट मीन्स दोज इवेंट्स which have at least some amount of overlapping in the features. Okay,
Okay.
तो ऐसे में for the task I will be using sigmoid activation function, क्योंकि और दोनों का अलग अलग क्लासेस के लिए, तो वहाँ मैं लगाऊंगा यार ये कितना है और ये इतना है, तो वहाँ मुझे दो नोड अलग बनाने पड़ेंगे, आई नीड टू वन नोड पर क्लास लेनी पड़ेगी वहाँ पर भी. इफ
Okay.
यदि ऐसा नहीं होता, बाइनरी होता, तो ओनली वन नोड ही लेता मैं आउटपुट लेयर पे, बट हियर इन आउटपुट लेयर आई नीड टू टेक वन नोड per class if there is a problem of multi-label classification, because I'm getting some similarities between the output.
Yeah.
Okay,
Okay, sir. Got it, sir.
okay, so this is inclusive. Any other doubt related to the activation function? What now you'll understand, these are the activation function, which activation function I need to use on the input layer, which activation function I need on to the output layer. I hope you got this point. Okay,
Yes, sir.
okay, so let me stop
Yes,
the
sir.
recording.